Here in section 8.3, we're going to look at a couple of applications in physics and engineering, but most specifically, we're going to be looking at the problem of moments and centers of mass. In this section, there are other topics that are explored, but this is going to be the one that we're going to focus on. Our main objective here is to find the point P on which a thin plate of any given shape balances horizontally. This point is called the center of mass or center of gravity of the plate. Notice that here this plate could come in various shapes, but we're assuming that it's a uniform thickness and it's a uniform density throughout. And we want to find the point on that plate that will allow it to balance. So to start, we'll think about a much simpler version of this, which is to take two point masses, say M1 and M2. We want to find the center of mass between them. So imagine they're attached to a bar of a particular length, and we want to find at what point can we balance those two masses on this bar. Okay. And the principle that governs this law is that the first mass times the distance d1 to the fulcrum where it balances should equal to m2 times the distance d2 to the fulcrum so d2 being the distance from the fulcrum to m2. So let's start by imagining that these two masses lie on an axis, where here we'll call the fulcrum x bar. That'll be the location of that on the axis. We'll say the location of M1 is x1, and the location of M2 is x2. So now thinking of these as points on a line, we can think of D1 as the distance from x bar to x1. So it's x bar minus x1 for D1. And D2 will be the distance from x2 to x bar. So it'll be x2 minus x bar. Okay, so now we know, according to our principle here, M1 times D1 should equal to M2 times D2. So we have M1 times x bar minus x1 equals M2 times x2 minus x bar. So we have M1 x bar minus M1 x1 equals M2 x2 minus M2 x bar. I'm going to try and isolate x bar in the equation here, so I'll move the terms that have x bar into the left-hand side here, and move the other terms to the right-hand side. Factoring out x bar, we have x bar times M1 plus M2 equals M1 x1 plus M2 x2. And so we see x bar will be M1 x1 plus M2 x2 divided by M1 plus M2. Okay, so that tells us now at what point we can locate the fulcrum. So given these two point masses at locations x1 and x2 along some axis, this formula here, M1 x1 plus M2 x2 divided by the sum M1 plus M2, tells us exactly where that fulcrum x bar will be located. So now to extend on this a little bit further, now suppose we have n point masses sort of scattered on some axis here. Here I'm just writing them in order, but not necessarily in any order here. And we want to know where's our x bar, our fulcrum, going to be located that'll allow us to balance this. And so the principle is essentially the same. It can be shown that if we sum up all these m1 times x1, so in other words, each mass at each point here has a particular coordinate that tells you its location. So multiplying the mass times its coordinate, these are called moments. So mixi is called the moment. And then summing up all the moments, and then dividing by the total mass, so the sum of all the masses, essentially extending on the formula that we showed in the previous slide. So what we're calling the moment of the system is just the sum of the individual moments, mixi. And in particular here we're saying the moment of the system about the origin. And by origin here we mean, we're looking at a collection of x values that land on a number line. So origin would be where 0 is on the number line. So all these xi's here essentially give us the distance from each of those individual point masses to the origin. Okay, so that's why we're calling it the moment of the system about the origin. Okay, so to extend this a little bit further, we can think about now the moments about the x and the y axes. So what we're calling, so now we imagine we've got point masses that are located at different coordinates in the xy plane. Okay, so to visualize here, we've got some point m1 located at the coordinates x1, y1, some other point m2, the coordinates x2, y2, and so on. Maybe you've got a third mass m3, the coordinates x3, y3, and so on. So we're looking at a collection of these masses in the xy plane with these coordinates given. So if I am looking at the moment of the system about the y-axis, I need to, so we're going to call this my, so I need to sum up their individual distances to the y-axis. So here the distance from m1, the first mass, to the y-axis will be x1. And the distance from m2 to the x-axis will be x2. And the distance from m3 to the x-axis will be x3. So we're summing up now the mass times its x-coordinate to get the moment about the y-axis. Okay, so notice we're calling it my here. So it's a little bit subtle there why we're calling it my, but it's because here the x-coordinates, xi's, give the distance to the y-axis. And in a similar way here, if I'm getting their distances to the x-axis to get their moments about the x-axis, we're going to use the y-coordinates. So now if I'm getting each of their distances to the x-axis, we're going to use the y-coordinates. So now the moment of the system about the x-axis, we'll be using the y-coordinates here. So mx, we're going to use yi, which is the distance to the x-axis. Okay. And so in this case, then we can get the x and the y coordinate of our center of mass by computing the center of mass for x bar and y bar separately. So to get x bar, we'll use my, the moment of the system about the y-axis, divided by m, and then to get y bar, we'll do mx over m, so the moment of the system about the x-axis divided by m. So this is a little bit, again, a little bit backwards. X bar here goes with my over m, y bar goes with mx over m. Just maybe an easier way to remember it is we're summing up all the mixi here to get x bar. And here to get y bar, we're summing up all the miyi and then dividing by the total mass. Okay, so let's make sense of these center of mass formulas in an example. Suppose we want to find the moments and center of mass of the system of objects that have masses 3, 4, and 8 at these 3 points here. So this first point is where m1 is a mass of 3 at this point -1, 1. We'll call m2 the mass at the point 2, -1, which has a mass of 4. Okay. And then the third mass has a mass of 8. So m3 equals 8, and it's located at the point 3, 2. So let's maybe just graph these points really quick to visualize what we're doing. So at the point -1, 1 is where my m1 goes, and that has a mass of 3. 2, -1 is where my second mass goes, and it has a mass of 4. And then point 3, 2 is where my third mass goes, and it has a mass of 8. So we can imagine that the one that has the largest mass, one that weighs the most of these three, is probably going to be where the center of mass is shifted towards. So we can imagine our center of mass is probably going to lie somewhere in between these 3 points, perhaps closest to the most mass, which is at m3. And let's solve out each of their individual moments. So we know my will be the sum of all the mixi over m. So we'll multiply each of the mass times the x-coordinates. So 3 times -1 plus 4 times 2 plus 8 times 3, and then divide by the sum of the masses, 3 plus 4 plus 8. Okay, so I think that would give me here -3 plus 8 plus 24. And then 3 plus 4 plus 8 gives me 15 downstairs. So this gives me, I think, 29 over 15. Okay. Oh, and actually, sorry, I did my over m here. So this is really computing x bar. So 29 is the moment, right? Actually, I should clarify here. My is really just 29. But the center of mass for the x-coordinate is at 29 over 15. Now let's compute y bar, which will be mx over m. So it'll be the sum of all the miyi over m. So we'll multiply each of their masses times the y-coordinates. So 3 times 1 plus 4 times -1 plus 8 times 2, and then divide by the sum of the masses. Again, here it says 3 minus 4 plus 16. I think here we get 15 over 15, which is, of course, 1. And so that's the y-coordinate of our center of mass. And notice here that the moment about the x-axis mx is equal to 15. Okay, but here the important thing is, where's our center of mass located? So here's our center of mass. It's located at the point 29 over 15, comma 1. And let's see, where does that land here? So 29 over 15 is perhaps a little bit less than 2, comma 1, so maybe something around right there is where our center of mass is. Okay, so somewhere in between these 3 points, and slightly closer to the heavier mass.